Welcome to this segment on review of basic electric circuits. And in this segment, we'll look at convention and symbols. We'll look at how we can use phasors. And we'll also talk about real power, reactive power, and power factor. And then we'll also talk about inductive and capacitive loads. So let's start with convention and symbols. We will use so-called MKS units, and we will make use of lowercase letters like voltage and current designated by these lowercase symbols for instantaneous quantities when they are functions of time. So even though we may not show explicitly that they are functions of time, they are functions of time. And then we'll use uppercase letters for average and in AC case RMS values. And we'll always have subscripts associated with these voltages and currents. So you can see here that this is this voltage V sub A, which is showing the potential of point A with respect to ground. And similarly, this current I, here it may be called just I, or you may want to give some subscript. But certainly for voltage here, VAB, it defines the voltage of point A with respect to B. So VAB is basically equal to VA minus VB. And to talk about these voltages and currents, it doesn't really make sense unless we define the voltage polarity and the current direction. So we have to be very careful in carefully defining those. So now let's look at what happens when we are dealing with sinusoidal AC voltages and currents in steady state. Okay, so let's say that we have a voltage, and let's think of this as time 0 over here, some point over here. And so if that's because on the horizontal axis we are plotting omega t. So as you can see here that the voltage, which is this waveform here, this one here is the voltage waveform. It can be written by this expression here. It has some amplitude V hat cosine omega t because of the way we defined our origin omega t equal to 0. And then we see that the current, which is defined by this waveform over here, this one over here, it doesn't start up to this point here. And you can see that this can be defined as some peak times cosine omega t minus phi, because phi is the angle by which this current is lagging behind this voltage. Okay, so phi, if you measure it from this point, it's this over here, or you measure from this point, it's this much over here, phi, right here. So these are the time domain expressions, but we can express them in a phasor domain by defining a voltage vector, which in this case we will first of all represent by uppercase symbol, and then we'll put a bar on top. So that designates a phasor, and since it was peaking at time 0, it is all along the real axis. That's where it will be. And you can see that it has an amplitude V hat. In this course, we will use the peak value to designate the amplitude, and because sometimes it's RMS that is used, but here in this course we'll use the peak, and the angle associated with is 0 here. Okay. Similarly, the current here, this current phasor, its amplitude is I hat, and since it's lagging behind by this angle phi, the angle associated with this is minus phi here, like this here. So you can see that this time domain expression corresponds to this phasor expression. Similarly, this time domain expression corresponds to this phasor over here. So we'll see the validity or the usefulness of this phasor representation by taking this very simple example. Let's say you have an RLC circuit, and you apply a sinusoidal or cosinusoidal voltage, and let's say it's in steady state. And then I ask you to calculate what the current would be as a function of time. Well, what you have to do is you have to write this equation here. So it has a differential term here. It has this integral term here. So if you change this to all differential, then it will be a second order differential equation. And you will have to solve this second order differential equation in time domain in order to get this current I of t. But that could be quite cumbersome. But more importantly, we'll see that doing it in phasor domain, it gives us some extra information. So let's start. Let's say that this is the voltage that's given to us. And then we have this resistance. This inductance turns into a reactive, inductive reactance, J omega L, like this here. And the capacitance turns into a reactive capacitance minus J 1 over omega C, which we can call minus J X of C. Okay, so what that means is the impedance of these three elements in series, this impedance Z, which is a complex number, is the sum of these three. So it's written in this form. It has an amplitude Z, and it has this angle phi. And this magnitude Z we can calculate by knowing that this is R is the real element, a real term, and then we have two which are imaginary terms. So as you can see immediately that this is x sub L here, and this here is x sub C over here, and so you can find this magnitude of this impedance, and you can find the phase angle associated with this impedance to be tan inverse of what's in the imaginary term divided by the real term over here. So graphically you can show this as well. If you have in this complex plane, R is along the real axis, then along the imaginary axis you have this JXL, and this minus JX sub C is in the opposite direction. So taking these two terms into account, you get this quantity over here along the imaginary line, and then imaginary axis, I should say, you have this much along the real axis, and the impedance then Z is over here, which is a complex number, right? So it has a magnitude, it has a phase angle here. So to find the current, what we have to do is just take this voltage phasor divided by this impedance, which will have this magnitude, and it will have this phase angle of minus phi, because Z, which has an angle phi, is in the denominator, so it shows up as minus I. So that's the current in phasor domain, and the meaning of this current in phasor domain in time domain is this amplitude of the voltage, which is V hat, divided by the magnitude of the impedance times cosine omega t minus phi. So minus phi comes from this angle over here, right? So rather than going and solving that second order differential equation, we can just do this in phasor domain, and we will have we will get the expression that we are looking for. The important thing to remember is that this voltage is a phasor, this current is a phasor, but this impedance Z is not a phasor. It's just a complex quantity here. So the next thing we will look at is the instantaneous power flow in an AC circuit. So let's say that you have two subcircuits, 1 and 2, and they are connected to each other. And let's define this voltage across them as here with this polarities, and the current with this direction as shown over here. Okay, so you can see that the average, the instantaneous power that is flowing from subcircuit 1 to subcircuit 2 is just the product of this voltage times this current given by this expression here, where let's say that this voltage is, these are all sinusoidal quantities. It has some amplitude and it has some phase angle over here. Similarly, this current I has some amplitude and some phase angle, phi sub I, but these are all cosinusoidally varying quantities. And we are looking at in this scheme, let's say in steady state. Okay, so let's take a case where the voltage and current they are both in phase. What that means is the angle associated with the voltage is the same as the angle associated with the current. And you can see that this solid line here is the plot for the voltage, and this is the plot for the current over here. Okay, they are in phase. So when you multiply these two together, you have the power, and this power you can see with the dotted curve over here, dashed curve, and you can see that it's varying at twice the frequency. So you have a certain frequency of the voltage, certain frequency of the current. They are the same frequency, but this power is pulsating with twice the frequency. And it has an average value. See, it's going to 0 and then going to this peak value back to 0. So it has an average value right in the middle over here. And so that's what we will designate by this average power P over here. And you can see that this average power would be maximum for a given voltage and current when voltage and current, they are both in phase. Okay, because in this case, the power, instantaneous power, although it pulsates, it just touches 0. It never goes negative. Okay, so now let's take a case where the current is lagging behind the voltage by an angle phi. Here I'm plotting with respect to time. So in this picture, I'm showing that the current is lagging behind the voltage by this time phi divided by omega, which is the frequency in radians per second at which these voltages and currents are lagging. So in this case, voltage and current, they are not in phase, so that's why we call them out of phase, where these two angles are not 0. And in this particular case for which this drawing is done, the current is lagging behind the voltage. And here what we see is that power flow reverses periodically. That is, every half cycle, this power here becomes negative here, right? So it's mostly positive, but it does become negative for a certain interval of time. So in this case, if you calculate for the same given values of peak voltage and peak current, you'll see that the average power that we come up with, which is plotted over here, this average power is P, would be less than what was maximum possible in the previous case, where voltage and current, they were in phase here. So what we need to do is to define something called, in addition to this real power, which we'll designate by symbol P, is something called a reactive power, which we'll designate by a symbol Q, and also then we'll define something called power factor. So first of all, we'd like to define a quantity called complex power, which is really the product of the voltage phasor and the complex conjugate of the current phasor. Okay, so if you do that, and if you remember the expressions for voltage and current phasors, you will see that this will be equal to voltage times, and here I'm taking the RMS voltage as the amplitude of these phasors. So it's the RMS voltage times the RMS current times the angle that would be the phase angle of the voltage minus the phase angle of the current. Okay, and that's the difference between these two angles that we'll call this angle phi. And you can see that the complex power would have a real term. We'll call the real power. We'll have an imaginary term. We'll call Q over here. And of course, it has a magnitude, which we'll call apparent power, as we'll see later on. And an angle associated with this would be phi. And phi is the same angle by which the current is, in this case, where the drawings are shown, is lagging behind the voltage. So from this expression, you can see that the real power would be the product of voltage, RMS current, times the cosine of this angle. Reactive power would be the product of voltage and current times the sine of that angle. And the units of real power, of course, would be watts. But for the reactive power, it is volt ampere reactive, VAR here. And then we have this apparent power, which is just this apparent power is the product of RMS voltage and RMS current. And that you can see from this complex expression would be equal to P squared plus Q squared square root over here, like this. And the units are volt amperes. So in phasor diagram, graphically, this voltage phasor is shown here. The current phasor is shown here. The difference of the two angles is equal to phi. And you can also see that we can draw this power triangle where P is along the real axis, the Q is along the imaginary axis over here, and the sum of these two, vector sum, is the complex power S here. Okay, and this angle phi is the difference of the voltage angle minus the current angle. And the power factor is the real power divided by the apparent power over here. So if you can plug in the expression for P, it's VI cosine phi. And if you divide that by the apparent power in the denominator, which is shown here, you just end up with cosine phi. Okay. So the power factor is really cosine of the angle between the voltage phasor and the current phasor. So in this slide, everything was done in terms of RMS voltage and RMS current, but we could have done it in terms of peak voltage and peak current. We're recognizing that peak voltage is just square root of 2 times the RMS voltage. Similarly, the peak current is in sinusoidally varying quantities. This is true only of sinusoidally varying quantities. RMS value times square root of 2. That's the peak value over here. So we can work with RMS or we can work with peak, but I think in this course, mostly we will deal with the peak values as defining the amplitude of the phasor expressions. So let's say you have an inductive load, like an RL load over here. Okay, so this is our load impedance over here, which has this angle phi, which will be positive here, because Z is equal to R plus J XL over here. So this is J XL, and this is R over here, right? So the current in this circuit, if you had some voltage here and this current I here, the current would lag this voltage by an angle with the same angle that you have for the impedance. So this Z has a magnitude and this angle over here. So the current would lag by this angle phi over here. And then we will call this a lagging power factor, that this load operates at a lagging power factor where the current lags the voltage. And in this power triangle, when you draw P and Q and S over here, okay, this angle phi is the same as the angle of this impedance over here. Okay, so that's what this is telling us. We say that this load, this RL load, draws reactive power. So Q that is being drawn here is positive. Okay, so this load would draw P as well as Q, and it's drawing positive reactive power. But please note the expression draws reactive power here. And most of these loads are inductive, particularly motors and transformers. But whatever I've said here for an inductive load would apply for a capacitive load, where let's say you have a load like this, and this is a capacitive load. It could be a pure capacitor, no resistance, but here the current would actually lead the voltage by some angle phi, and you can say that instead of drawing reactive power, such a load would supply reactive power. So this brings us to the summary of this segment, where we have looked at the conventions of specifying voltages and currents and the symbols, and we have looked at use of phasors. We have looked at power, reactive power, and power factor, and we have also looked at inductive and capacitive loads.